Good morning, good afternoon, or good evening, as the case may be. I'm Barry Wise, president of Eigenvector Research, and this is everything you need to know about how to do principal components analysis. And today, our presenter is our technology principal, Bob Roginski. I always wonder why Bob picked the name principal. Did you always want to be a high school principal, Bob?
No.
Okay. But Bob's the guy in charge today. And the way we normally do this is everybody stays muted, but if you have questions, please ask questions in the chat. We have several of the Eigen guys here. I see Lyle's here, Donald's here. I'm not sure who all the Rasmus is here. And we will try to answer questions for you in the chat. And if there are questions that I think everybody would be interested in, then I will ask Bob. I'll interrupt him, and we'll get those covered. And we will post this recorded video of this online in the next couple of days, and we'll let you know where it is. And have I missed anything, Bob?
No. In fact, you've covered the first three bullet points here on this note slide, and the final thing that I'll just mention is I'll be using PLS Toolbox 8.9.1, the most recent release, but I'll be using the user interfaces only. So everything that I'll be doing today will apply to using either PLS Toolbox or Solo.
Okay, well, it sounds great. Take it away, Bob.
All right, thanks, Barry. So in terms of what we want to cover in this webinar today, principal components analysis, we're going to start off with a rather brief primer. If you've never done PCA before, the hope is that with the primer, it'll at least give you a flavor of what all PCA does with your data, what some of the outputs are, and the motivations behind PCA. And then, but certainly we do recommend, if you're interested in delving into this further, we do have online training which is available. And those of you who are already well versed in PCA, just bear with me as I go through the primer. And then we're going to have a couple of example data sets which we will show. And we're going to focus on bringing the data into the PCA interface, building some models and looking at the results and also associated information relevant not only to the original data set itself, but also the results that we get from PCA. As Barry mentioned, please ask any questions, anything that comes up along the way, relay them through the chat channel on the WebEx, and Barry and the other Eigen guys will be looking closely at that and relay those to me if they're of general interest, or oftentimes they will answer the questions themselves through the chat channel. So principal components analysis. We really like principal components analysis. In fact, for myself, it's a jack of all trades and a master of not much. And I don't mean that in a denigrating sense. It's a very valuable tool that whenever I start a new consulting project, or I'm just even just starting with looking at a new set of data, principal components analysis is the first tool that I will use because it does many things. It provides insight on the relationships between samples, or otherwise known as observations, and variables. Those are the measurables. Those are the things that we're actually measuring on each of the samples. It's an effective tool for reduction in the dimensionality of the data. And this is really important to a lot of data analysts, but in particular We work a lot with spectroscopic data, and even with a moderately sized data set that is, say, 30 samples by 1,000 variables, not all that unusual, you have 30,000 different pieces of information there. And, sometimes you can identify trends or relationships through overlay plots with that data set. But PCA is just really helpful at distilling the information that's available in that data set and being able to tap into that with a small number of plots. Principal components analysis is very helpful at uncovering correlation structures within your data. You'll find oftentimes that there's typically there's typically several correlation structures within your data set, depending upon how large and how complex your data set is. And PCA just does a nice job of separating those out one from another so that you can focus on what is it that's contributing in your data to a particular correlation structure. PCA can be used to filter noise in your data. One of the things that PCA ends up doing for you is to partition your data between sources of systematic variation and variation that's more of random noise. Now, the separation between the two is not perfect, but it can be readily used to help clean up your data in this mode. And as I mentioned before, it's an extremely valuable first option in reviewing your data. So what is it that PCA does? And we're going to start here with a very simple data set. It's a system of observations represented by the green circles here in a two-variable system. I'll call them X1 and X2. And we're going to work with the assumption that our data is centered. So the actual center of our data is the origin of our X1 and X2 axes. And I will postulate here that PC1 is a line that is a particular direction in our data that has a number of helpful and interesting properties. Well, how do we obtain this PC1? Well, let's do a little variation here, and let's just draw an arbitrary line in our two-dimensional space here that goes through the origin. And for each of the data points in our data set, we're going to project each of those points onto this line. And what do I mean by a projection? It is a line from that data point which is orthogonal to this blue line of interest. So I'll do that for that data point there, one here, one here. And as we go on the other side of the origin, you can see I'm focusing on the data points which are rather far away from the blue line. So I've got 6 of my data points here that I've drawn projections from the data point to this blue line. I'm going to represent each of these dashed lines as E sub I, residual or error or lack of fit. And I'm going to be interested in the length of each of these. And in fact, I'm going to come up with a metric where for each of my data points, I determine the length of each of these projection lines, the red dash lines, square them, and sum them up over all the data points. So with this blue line, I'll have a certain value for this metric. Now let me go ahead and take this blue line and rotate it. And I'll repeat the process by drawing projections from data points. And here I'm you get the picture. So I'm doing less data points here. But the same idea holds. I'm going to represent each of these projections as E sub i's, determine the length of these, and then sum and square them. Okay, so I have a degree of freedom with respect to how I choose to rotate this blue line. Well, what is it that's special about PC1? PC1, principal component number 1, is the line that minimizes this metric. It is the line which minimizes the sum of squares of the perpendicular or orthogonal distances for all of the observations to that line. Another property that PC1 has is it captures the most variance in my data. And what do I mean by captures the most variance? Well, as I project each of these points onto that line, I have these measures that we'll get to in a little bit called scores, and I can calculate the variance of the scores in that direction. And PC1 maximizes the scores for our data when projected onto that line. So one of the key components here is a loading. What is a loading? Well, a loading is how is PC1 constructed from X1 and X2. PC1 is a linear combination of our original variables, X1 and X2, and that's shown here. So PC1 is a line which is made up of so much of X1 and so much of X2. Now, I want to change my tool here. Here we go. Now, I could have drawn, this is the makeup of PC1. So these could be the loadings. And, it turns out, going back to your trigonometry days, it really doesn't matter because the ratio of how much X2 to how much X1 goes into making PC1 is going to be constant because this is at a given angle in my X2, X1 plane. And as it turns out, at least in our software, the loadings are normalized so that they will have a length equal to 1. Now, one of the other key components in PCA is a score. The score is a distance from the origin to the projection of a given point to a particular principal component. What do I mean by that graphically? So we have our collection of data here in the green circles, and we have PC1, which is defined either on the basis of minimizing the sum of square of the orthogonal distances or capturing the most variance. The two end up being equivalent. Let's focus on this particular data point here. So if I were to project this data point onto the PC1 axis, sorry, not a very straight line there. This is the projection on this is the projection of that data point, which I just made disappear on the PC1 axis. So the score for that observation on PC1 is the distance along PC1 from the origin to that data point. How about higher PCs? Well, one of the very helpful properties that we have with respect to the principal components is that they are all orthogonal to each other. So PC1, given that PC1 is in this direction, and we're working with a two-dimensional system here, PC2 can only be in this direction, or we can choose it to be in the opposite direction. There is an ambiguity with respect to sign. Principal components are ordered in the amount of variance captured. We mentioned before that PC1 captures the most variance in our data. PC2 is going to capture variance in my data, but it's going to be less than that captured or explained by PC1. And as we go to higher dimensions, higher dimensionality data, this still holds. So PC3 is going to be orthogonal to PC2 and PC1, and PC3 is going to capture less variance or explain less variance than either PC's 2 or 1. What do my scores look like for PC2? So if I were to take this point out here and project it all the way onto my PC2 line and zoom in, so this is the point at which the projection from that point that was originally out here falls upon my PC2 direction. So this distance here, that is the score for PC2. Now, if you go back to this picture, it should be pretty clear to see that numerically my scores for PC1 are going to be larger than what I see for PC2. And that ties in directly with this point here, with the principal components being ordered in terms of the amount of variance explained. There's a couple of other important outputs of a principal components analysis model, and we refer to them as diagnostics, and they help you to understand how relevant data is, especially new data, when your existing PCA model is applied to that data. And the first is the Q residual, and the second is Hotelling's T squared. And I'm going to show you what these look like graphically. So consider I had my observations here in the green circles, and I built a one PC model, one principal component PCA model. So my PCA model is this line. Now, why didn't I choose two? Well, two PCs, because it looks like to me, and if you look back at a couple of slides ago where I actually drew PC2, the variation in PC2 looks to be noise or random variation, whereas I definitely have a systematic source of variation along the source of PC1. So what I could say is that, what I'm interested in pulling out from this data set is really the systematic variation in PC1, and I'm going to ignore the other direction, the other source of variation. So now my model is already defined, and I have this new observation that I apply the PCA model to, which is this red circle. Now the red circle is almost on the line, on the blue line, not perfectly, but not very far off of it. Certainly not far off relative to the other samples. So this would be a sample which is well explained by my model. So it has a low Q. It has a small orthogonal distance from the data point to the model. It has a high T squared. why is the t-squared for this sample high? Well, when I project this point, bring the pen back up. When I project this point onto the model, the distance from the projection to the origin is quite a bit larger than any of the other corresponding projections from my calibration data, the data that I use to build the model. Let's look at another observation. So I have a new sample here, and when I project it onto my model, that distance is relatively large. And you can get that right off the bat by noticing, well, this point is pretty far off of this line. It's not explained well by this model. So it has a high Q residual because this distance is quite large, especially relative to the green calibration samples. This sample has a low t-squared, however, because when I project it into my model, into this line, its projection is right in the mix with the other samples. It's actually fairly close to the origin. There's several calibration samples that have projections which are higher than this red sample. Now, if I go in the other direction out here, this is a sample which is quite far from the blue line, has a high Q residual, not explained well by the model. And when I project this point into my model, or onto my model, its projection is far from the origin relative to the other samples used to make up this model in an opposite direction from the sample here. But this is a sample that kind of has the double jeopardy aspect to it. It has both a high Q and a high t-squared metrics. When these are going to be key for you to look at when you are applying your principal, your PCA model onto new data, because the PCA model will return for you scores which tell you where the projection of that point resides relative into your model space. But in particular, the Q residual is going to tell you, is that measurement really, does it fit in well with the data that was used to build the model? Any questions so far, Barry?
No, Bob.
All right.
Not seen. Oh, hey, we have one. How do Q and t-squared relate to leverage and/or Mahalanobis distance? One just came in.
So the t-squared is a form of a Mahalanobis distance in that the t-squared is calculated on the basis of the scores and not the original data. So Mahalanobis distance is a general distance metric which is scaled according to how your data is shaped, or scaled to the variance in each of your variables. T-squared is one step further in that instead of using the original data to calculate this normalized distance, we are using the scores in our data. Now, if we were to extend this to 3D, so now I have a system with three variables 1, 2, and 3. And what we're trying to show here is a system, or our calibration data, or our data used to build the model, are the red circles here. And the data happens to reside pretty much in a plane. So it's there are three variables in the system, but my red observations or circles are within a single plane. Now with PCA, principal component 1 is going to be the direction that captures the most variance in my data. And the way that my data is arranged for building the model, it's in the form of an ellipse. So PC1 is going to be coincident with the major axis of this ellipse, and PC2 is going to be orthogonal to PC1 and captures the second most variance. PC3 would be orthogonal to the plane containing the data and would have very little variance if it would have zero variance if all of my data points were exactly within a plane. If I had little excursions above and below this plane, then PC3 would capture some variance, but we would consider that relative to PCs 1 and 2 to be small and probably noise. If I bring in this green observation here, which is above the plane of the red circles here, well, that's a data point which is not well explained by my model because it does not reside within the plane of the model. And in this example, we've moved to a PCA model which now has two components. As I project this point into the plane, however, its projection is rather on par with the other samples, the calibration samples. In fact, it's well within this 95% or this confidence ellipse, which is formed by the two principal components. Now, if I have this observation out here, and this is meant to show that this point is within the plane of these other measurements, but it's kind of right at the border of the edges of the two ellipses. So a little bit off there. So this is a data point which is that is within the plane, but it has an unusually large distance from the origin as the other samples do. So this is a sample that would have a low Q because it is within the plane. It's explained well by the model, but it has a high T squared. Okay. Some helpful properties. PCs are ordered in the amount of variance captured. PCs are orthogonal. And recall that our PCs, all of them, are constructed as linear combinations of our original variables, and this we refer to as loadings. If our data is centered, it also turns out that our scores are orthogonal, which is a helpful property. We can calculate as many principal components up to and including the mathematical rank of the data, but we typically end up using far fewer. So what I mean by that is if I have a data set of spectroscopic data, 30 samples, 1,000 variables, the maximum the rank could be for that data set is 30 because it's the smaller of the two dimensions. So we can calculate up to 30 PCs for that data set, but more than likely we're going to use far fewer. Okay. All right, we're going to jump into the first of the two examples that we'll be taking a look at here. And this is a data set which is included in the software known as gasoline octane. And it consists of a series of 39 gasoline samples near our absorbance spectra obtained over the range of 1100 to 1550 nanometers. There's 6 samples which have alcohol added. And we want to use exploratory analysis, use PCA, and ask the question, is it possible to see the source of the signal, which is related to octane? And for this, we're just going to mean center our data. So I'm going to, no, I don't want to keep my annotations. I will switch over to the software. So if you are using Solo, the workspace browser will be the first window which comes up when you launch the application. If you're using PLS Toolbox, you would start MATLAB and then type the word browse at the command line, and that'll launch the workspace browser. And as I mentioned, everything that we will be doing in the webinar today will be using the user interfaces. If I go down to the section entitled Model Cache, and if I expand on the item demo data and scroll down, I'll see an entry here, octane rating by near IR spectroscopy. After I click on that and drag it into the workspace, this is a file that actually contains two variables. One is the variable named spec, which is going to be the actual spectroscopic data for my 39 samples. And then a variable called octane, which is the octane rating for each of those samples in the spec data set. I'm going to start with spec and click and drag that onto PCA over here under Analysis Tools. That'll launch my analysis interface. Yours may look a little bit different than what I have here. I've turned off the model cache, which that's a topic that we won't touch upon here. And then also there is a flow chart which is available for helping, especially if you're first starting out building models, that kind of gives you a little guide on what to do first, load the data all the way through building the model. But I'm just going to focus on the analysis interface shown here. So as I notice, as the title of this window, Analysis PCA, it has the name of the data set. No model means that a model has not been constructed at this point. Now, if I mouse over the button here entitled X, that corresponds to the X block. That's the data that I actually loaded. And I did that by dragging the data set from the workspace onto the PCA tool. We are big advocates of looking at your data first before you do anything, before you try any modeling. And that's exactly what we're going to do here. I'm going to right click on the X block here and generate a plot. Drag that over here a little bit. And the second thing I'm going to do is to right click again and select Edit Data. And that's going to open up this data set in our data set editor. We recently had a webinar on getting started that I invite you to take a look at, where we talk quite a bit about the dataset editor. Simply put, the dataset editor is a custom object that we've developed at Eigenvector. Think of it as a container that holds your raw data in a spreadsheet fashion like here, but also contains the associated metadata. In fact, if I go over here and click on row labels, you can see that I have a label for each row in my data set. And that's helpful for plotting. I can choose to show labels on my samples. But then we also have this column here called class. And we'll get back to that in a little bit. The plot that I generated here, it shows mean versus wavelength. And this is actually a summary plot that shows the mean response for all of my samples across all of the variables. And this wavelength information actually comes from, it's contained within the data set. But I'd like to do an overlay of all the data, and that's done easily just by clicking on Data. Why are we such big proponents of plotting your data? Well, for the most part, you're going to be the subject matter expert on the data that you are going to analyze, and you are the best person to judge, at least at a first pass, whether you have any egregious outliers in your data set. If I had a response here, a single sample that had a response at 0 across all of the variables, well, that's a sample that doesn't really quite fit in. And I'm going to go ahead and exclude that sample in the first place because it, first off, it looks to be a sample or measurement which would be in error, and my results are going to be skewed by the presence of that sample. So get rid of it. Now, you might say that in looking at this data that I've got, everything looks pretty normal. Nothing jumps out as looking unusual until I get to around 1400 nanometers, and some of these samples start to diverge from the rest. Well, it actually turns out if I turn on my sample classes and put on a legend, those are the green samples, and those are the samples that are gas combined with alcohol. Where did this information come from? It's in this class column here. And in fact, if I scroll down, I could see here that my last 4 samples are gas with alcohol. Okay. But the first thing that I want to do is I want to see, without the impact of the samples with alcohol, can I identify any trends in just the strict gasoline samples of the octane rating? And I could do that from the dataset editor here. If I right-click on class and choose select class, and now I select the samples gas with alcohol, and then from the main menu in the dataset editor, edit, exclude selected. So now that's going to turn off, for viewing purposes, the gas with alcohol samples. And I could turn off the legend. It's not really helpful here. And I'm going to turn off the class coloring because I'm looking at samples which are all from the same grouping. But now I'd like to look at some trends. Well, it'd be helpful if I have some information related to octane rating. And I can do that by using the color by tool here. If I click on color by, I can color these lines by various parameters, including a variable which is in the workspace. And to do that, I'm going to select load and then octane. So now each of these spectra are color-coded according to the octane rating for that particular sample. And I can do that by looking at this color bar. If I bring up the color bar, let's take a look at a couple of regions here. I'll zoom in here. So what we're seeing is, in this region between 1140 and 1160 nanometers, I have a reasonable trend of an increase in octane rating as I have higher absorbance. And now let me zoom out and look at this region. And in this region, between, let's say, 1180 and 1210 nanometers, it's the opposite trend. The lower the absorbance in this region, the higher the octane rating. Okay. Notice in my dataset editor that the samples gasoline with alcohol, this column here for include, those samples have been switched off. So I did not delete these samples of gas with alcohol before. All I've done is I've switched them off for plotting and also analysis purposes. I'm going to want to turn that back on. Easiest way to do that, if I right-click on the Include button here and select Clear/Reset, and it turns them all back on. And I can close the dataset editor and this plot. So we've made sure that there were not any egregious outliers in our data set. We did some color coding or color by of our plots to see a couple of regions that showed some good trends with respect to the octane rating. Let's build our PCA model on all of our samples and see what we get from the outputs there. If I right-click on this P here, this is the button which controls the pre-processing for the X block. I can choose Edit Pre-Processing, which will bring up a user interface. We'll get to that shortly. But right now, we're just going to use mean centering, as we showed in the slide. And the easiest way to get to that is from this Basic Methods menu. So you could choose None, Mean Centering, or Auto Scaling. I'm going to select Mean Centering, and then go ahead and build my model. The software comes up with a choice of 4 PCs, and there's a number of internal checks that are being performed to give you a good idea of what's a reasonable number of principal components to retain. And I'm going to stick with this 4. If I wanted to, let's say, build a 6 PC model, all I would need to do is to click on the 6th row and rebuild the model at that point. But I'm happy with 4 for the purposes of what I'm going to show here. And let's take a look at the results. The Erlenmeyer flask here, this button generates scores and sample statistics plots. So if I click on that, I get a figure with a series of 3 plots. And I want to focus on this middle one. If I double click on this middle plot in this figure, that'll generate a new figure with just that plot. I'll close this one. So my data appears to be color-coded. And that's because the sample information, which I had in my original data set, in particular, the class membership information, is retained. And now I'm showing scores on PC2 versus PC1. I have a 95% confidence ellipse going around my data. That's not really helping me much here because my data is certainly not very evenly distributed. So I'm going to turn that off in my confidence limits just so I can have my scores take up a bit more real estate here. And notice that, as I mentioned before, my samples are color-coded. And if I turn the legend on, you can see that the red diamonds represent the gasoline-only samples, and the green squares are the gas with alcohol samples. What is PC1 doing and what is PC2 doing? Well, PC1 is really separating my gasoline-only samples from the gasoline with alcohol samples. So it's fair to say with PC1, it's a direction in my data which tends to separate the one group of samples, the one class, from the other. Now, there's a little bit of variability in the gasoline samples on PC1, but in PC2, we're seeing much more of a spread in the gasoline-only samples. Well, how about the information related to octane? Is there some way that we can take advantage of that here? And what I'll do is I'll turn off my classes and turn off the legend. And I can use the same color by tool that I had before. I'm going to load that Octane data set from the workspace. And now that's going to color code my data. Recall that these samples here are the gasoline only, and there's a fairly clear trend that high scores on PC2 correspond to low octane rating. And as you go in the direction of PC2, you get higher and higher. Now, there's a couple that don't exactly quite fit the trend. This sample here is a good example. Now, if you're the gasoline with alcohol samples, it's a little bit more complex. You're in this direction overall, you have an impact of higher octane rating, but the octane rating is going to depend upon the octane rating of the gasoline feedstock that you started with, and also how much alcohol which you had added. And the samples did contain differing amounts of alcohol. So this gives us the information relative, or the scores tell us how our samples are arranged along these two directions. Well, what are those two directions? And to do that, I'm going to bring up a loadings plot. Loadings plot is from the analysis interface, and it's the icon which kind of looks like a spectrum right next to the Erlenmeyer flask. And when I click on that, it generates a plot with the loadings for PC1. These are so each of these is how much of my original variables are being used to comprise this direction in my data. And you can see it's dominated from the alcohol component. Recall that for the 6 samples containing alcohol, I had another peak showing up, and then a broad feature which extended. Now, how about PC2? So PC2 is dominated by this region here, and then this region here, but they're anti-correlated. But that's completely consistent with the information that we got when we plotted just the gasoline samples and colored them by the octane rating. As we had samples with higher and higher octane rating, the feature here would grow in size and the feature here would diminish. Now, this looks to be opposite from the trends that we saw in the overlay of the spectra, but note that the octane rating is anti-correlated with the scores on PC2. We could easily take this plot and flip it upside down and do the same thing with the scores. And then you would see, higher signal here would correspond to higher scores on PC2. We can take a look at scores on PC4 versus PC3. Notice I am still colored by my octane rating. And what I see here is I have a whole bunch of samples distributed pretty closely along this this horizontal axis here, where the scores on PC4 are close to 0. And in fact, I can turn my classes back on, and I see that, well, it's mostly my gasoline-only samples which reside along that horizontal axis. I do have one data point here belonging to the gas plus alcohol group, but the rest of them are above and below that horizontal axis. Notice, let's see, I want to turn off the legend. There we go. Sorry about that. Am I seeing a clear trend in PC4 with octane rating? Well, yeah, I do have the lowest one here. Maybe somewhat in that direction. PC3, there looks to be a trend in the octane rating, except we have a number of the gasoline only samples which don't follow that trend. So that is something that in subsequent review, I would like to take a look at the gasoline only samples which don't follow this trend in the octane rating and see what's different about them. My next step might be to exclude from the analysis the gas plus alcohol and then just focus on the gasoline only samples and see what makes these samples look different. Okay, so I'm going to move on to the next example, unless there's any questions about this one.
We're good so far.
All right, thank you. So if I close my analysis window here, that closes all the subsequent plots that were generated from it. And clear the workspace. It gets rid of the two variables which I loaded. And let me switch over to the slides. Just one slide to show here. So this is from the 2018 Chemiometry Conference challenge problem. It is a series of near-IR reflection spectra of over 3,900 samples representing many different agricultural products. The actual challenge problem itself was posed as who could build the best predictive model for protein content for this data, and then also for a related validation set. And that that turns out to be that's a regression problem, which we're not going to talk about here. But we will treat this as an exploratory analysis problem, taking a look at this data with PCA, and what information can we glean. I have the data set in a .mat file on my desktop here. And if I go ahead and click that and click on it and drag it into the workspace, I have two variables, one product spectra and the second protein. If I take product spectra, drag it on the PCA, very similar to before. I have a window which comes up, analysis, PCA, no model built, and the name of the data set. I'm going to change my pre-processing to mean centering and then generate a plot of the data. So when I selected plot, it gives me or provides me with a plot of the mean of all of the spectra. I click on data and give it a moment to update. So this is an overlay plot of the data in my data set, the over 3,900 samples. And you can see that there's a fair amount of baseline variation, and that's probably going to be something that I wish to address. But we're going to take a look at what PCA tells us with just mean centering. Now, if I turn on my classes, and bring up a legend, make that a bit bigger. Now you can see with the overlay plot, when I color code my samples by their class membership, I do seem to have some separation But again, a lot of my variance is the change in baseline from sample to sample is contributing a lot of variance, which typically is not going to be all that helpful for you. Okay. I do not see any what I consider to be egregious outliers in my data set. But it's a little tough to tell with this overlay plot and this much spread in the baseline. So we'll take a look and see what PCA tells us. My pre-processing is set to mean centering. I'm going to go ahead and generate a model. And for this one, I'm going to extend it to 4 PCs, and I'll show you why in a bit. So now my current number of PCs is 4. And I'm going to generate a different type of plot here. We just showed you a plot of the overlay of the data. Now I want to generate this plot here, plot preprocessed data. And now this is an overlay plot of all the samples with the preprocessing. And in this case, it just means centering. So all we've done is we've taken the average response from all of those samples and subtracted it off from each of the ones in the data set. And you can see we have the somewhat differentiation between the classes that we have before. And I'm going to keep that here for the moment because we're going to make some changes to the pre-processing and build additional models and show you what that does. Now, if I bring up a scores plot, and I'm going to focus on this bottom one, which shows my scores versus sample index. Close that plot. And you could see that scores on PC1 are showing some separation. So it turned out in this challenge in trying to build regression models for these agricultural products, you could build a global model. You could try to regress or fit protein values to each of the spectra on the entire ensemble of samples. But that global model ends up not being all that, doesn't perform all that well. Now we see in PCA here that we do have some separations between the classes, which shouldn't be that surprising because we saw some separations here in terms of the color coding. PC1 shows some separation between the classes, and I'm determining that by looking at, am I seeing breaks like from this group here, the scores on PC1 for the rapeseed. I can easily tell rapeseed from grass silage and maize WP just in terms of the scores on PC1. Now, if I take a look at the scores on PC2, I do see separation in the scores. And on PC3, more separation in the scores. And on PC4, by the time I get to PC4, I'm not seeing as much clean separation between my groups. So, I want to point out PCA is not a classification technique. All it does is it partitions variance into important directions. But these first 3 directions, PCs 1, 2, and 3, look to be important for being able to separate. Now, if I want to try to make these separations a little cleaner, I can try changing my pre-processing. So let's try and do that. This time, when I right-click on my preprocessing P, I'm going to select Edit Preprocessing. Mean centering is the method that I had before. Now I'm going to add a derivative. And the rationale for that is to try to reduce the amount of baseline variation that I have from sample to sample. So I'm choosing Savitsky-Golay derivative, a first derivative with a second order polynomial, filter width of 15. Those are default settings. And see where this gets us. So when I click OK, the first thing it does is going to update this plot here. And you see that that baseline variation has been drastically reduced. And maybe my separation between the classes is going to be a little cleaner. We can test that by clicking on Model. And now I can go through and take a look at my scores on PC1, PC2, and PC3. PC4, again, does not provide much in terms of the separation between the classes. Now, what I'm going to do with this plot is I'm going to make a duplicate of it. And if I type the number 3 in here, it's going to make it that figure, it's going to modify that figure to have 3 plots. And here I want to put the scores on PC1 on the middle, scores on PC2, and on the last one, scores on PC3. And I'm going to make what's called a static view of that plot. So this is a plot now, it's an exact copy of this, but it's not going to change. As you saw, these other plots are linked to the analysis window and will change when I make changes to my analysis. I'm going to move this off of the screen for now. Move this over. And now on my last plot, or my last iteration here, I'm going to add multiplicative scatter correction as a preprocessing method. Why am I doing that? Well, these are reflectance measurements, and as such, they are measurements where you don't have a well-defined path length for each of your samples. And MSC is a preprocessing step which tries to put all your samples on roughly the same effective path length. So when I select that, my preprocessed data plot versus wavelength gets updated. And I can't tell anything definitively from here, except that it doesn't look to be worse. So let's go ahead and rebuild that model. So now this is scores on PCs 1, 2, and 3, and that is with the 3 preprocessing steps, MSC, first derivative, and mean centering. And this is the same except without MSC. And what I would say is that it has certainly tightened up some of the groups here in terms of the separations. It's increased the distance between some of the groups. Although this group here, this is the milk and that is the milk powder and whey, seems to be more spread out. So that's kind of the problematic group here. Now, we've mentioned diagnostics, but we haven't touched upon them yet. I'm going to minimize this figure and this figure. And over here, I'm going to turn off my class groupings and modify this plot so that on the vertical axis, I'm showing, wrong one selected. Here we go. On the vertical axis, I'm going to show Q residuals, and on the horizontal axis, Hotelling's t-squared. These are reduced statistics. So samples which have reduced statistics above 1, they at least bear some looking at. Although what I will say here is that we have reduced Q residuals going up to almost 7. So that's 7 times the 95% confidence limit for the Q residual. But I appear to have a continuum here. And in fact, if I right-click on one of these data points and do a histogram on the Y data, you could see that, yes, I do have samples which are above the 1.0, but it's what we're missing in this plot is that the bulk, the vast majority of the samples have reduced Q residuals below 1.0. Now I'm going to close this plot and turn the color coding back on, and you could see that most of those samples with the high Q residuals, those are milk powder and whey samples. And in fact, I can generate a plot, but in the interest of time, I'll do this offline and record it and add it to the material here because I've gone a little bit over. My apologies. But it's clear, you'll be able to see this from here, but I'll show you in the additional video how you focus just on the distribution of Q residuals for the milk powder and whey samples. So as I go back to the slides. So our summary, principal components analysis, it identifies important directions in your data based upon variance captured. It's not a classification technique. It's not a regression technique. It serves solely to identify those important directions in your data. Now, if you do end up with sample clustering for different groups with PCA, chances are really, really good that if your ultimate objective is to build a classification model, that you'll be successful. The converse of that statement is not true, however. PCA reduces dimensionality of complex data sets. So instead of looking at many samples and many variables, trying to parse through or to go through that step, you end up viewing your data with a smaller number of variables, that being the scores. And it partitions systematic variation, which we're usually much more interested in, from random variation. The steps that we conducted here: review the data, plotting. Select your pre-processing. We did not touch upon cross-validation. That'll be a subject for another day. But this is a tool that will help you to further identify outliers and to give you an idea of how many factors to retain in your model. And then once you build your model, then take a look at scores for relationships between the samples, loadings for relationships between the variables, and the diagnostics, in particular Q and T squared, to see whether your samples are unusual with respect to that model space. And with that, if there's any questions that we can address.
No, it just had just one or two that we took care of in the chat that were pretty simple. So we're pretty good on questions.
All right.
Yeah.
Well, thank you for your patience. This went a little longer than I had planned, but hopefully you're able to take something home that will be helpful for you in your forays into data analysis.
Yeah, this is a really good primer on how the method works here, Bob. So that was good. So your friends that want to know how PCA works, this is a pretty good resource for that. So let me just do a commercial here then. Our next webinar will be in 2 weeks and 2 days. What day does that put it on? The 22nd, I think. And we're going to talk about everything you need to know about how to do partial least squares regression. And so we hope that you'll join us for that. Okay, thanks very much.
Hi, this is Bob Roginski of Eigenvector Research. Just showing you at this point a little more detail surrounding looking at the Q versus T squared plot for the second example in the PCA webinar. This is from the Chemiometry Challenge dataset from 2018. In the class, we showed, or in the webinar, we showed Q residuals reduced versus Hotelling's T squared reduced. And we right-click on a data point, brings up a contextual menu, histogram on the Y data. And we noted that the number of samples having, let's say, reduced Q residuals higher than 1.5 is actually rather small. It'd be the area under the curve from this point on. And that kind of gets lost in this plot here. You look at, there looks to be a lot of samples having reduced Q residuals above 1.5, going all the way up to 7. But what the plot doesn't, the context you don't get is that there are so many samples having reduced Q residuals below 1.5. So that gets a little bit lost here, and the histogram certainly helps with that assessment. Now, I'm going to close that histogram window, and when we turn the classes on, you see that there really seems to be a disproportionate number of samples from the milk, powder, and whey grouping having that distinction of having high reduced Q residuals. And I can certainly create a histogram, again, on the Y data. And since I have classes which are being shown, I am going to get a histogram for each group. Now, this is a little bit of a busy plot because there's several classes, but if I turn on the legend here, you could see the milk, powder, and whey is the group that really is overly represented with having high reduced Q residuals. What if we wanted to get a little clearer picture of that? I will close that and turn that off. If I right-click on one of the samples from that group and choose Select Class, and right-click again on one of the selected samples, Include Only Selected. Taking a little longer than you would normally expect because I had the pre-processed X data plot still open. But now I have my Q versus T squared both reduced for only the milk, powder, and whey samples. And now if I right-click on one of the data points and generate a histogram, now you could see a lot more detail. It's not being hidden by or obfuscated by the other classes present in the data. So this shows you when you have your data set up in classes and you are viewing the classes, You can generate a histogram that's going to give you a distribution plot for each of the classes which are showing. And to further the point, if I choose to view only one or more of the classes in my data set, then the histogram will reflect which classes I have showing.